All right, let's talk about database replication. When you hear that term, you probably picture a really simple setup, right? A master database and a few slaves. Easy. But what if that simple picture is hiding a whole world of danger, of really tough engineering choices? Well, that's exactly what we're going to dig into in this explainer. So the textbook definition is pretty straightforward. You've got one database, the master, that's the single source of truth. It handles all the new information, all the rights. And then you have the others, the slaves, which are basically just read-only copies to help spread the workload. It looks so clean on a diagram, right? So efficient. But trust me, this neat little picture is incredibly deceptive. It hides all the messy details and everything that's about to go wrong. You see, this is so much more than a simple copy-paste job. It's actually a series of really difficult trade-offs that engineers have to wrestle with every single day. So today we're going to peel back the layers of this onion. We're going to explore the deep mechanics, the hidden dangers, and the tough choices that mean the difference between a system that works perfectly and one that fails catastrophically. Okay, so here it is, the first big secret, the first layer of our onion. You don't actually replicate data. You replicate events. Now, this is a huge mental shift. The key to all of this isn't copying files from one place to another. It's about perfectly replaying a sequence of actions, almost like a theatrical script. And the star of this show is the replication log. You might have heard of it as the binary log in MySQL or the write-ahead log in Postgres. This one file is the absolute central nervous system for the entire operation. Think of it as the official, unchangeable history of every single change ever made to the master database. It is the script, and all the slaves have to follow it perfectly. The whole process follows this really simple, kind of elegant flow. Let's just walk through it real quick. Step 1, a write comes into the master. Step 2, the master immediately writes that event down in its log. Step 3, a slave connects and says, hey, got anything new for me? And finally, step 4, the slave downloads those events and replays them on its own machine, in the exact same order. This simple 4-step loop is the bedrock for everything else we're about to discuss. Okay, so if the log is a script, then the obvious next question is, what language is that script written in? What exactly does the master write down for the slaves to read? This decision brings us to our very first major engineering dilemma. So there are two main languages, if you will. Over on the left, you've got statement-based replication, or SBR. It's super direct. It just sends the literal SQL command that was executed. And this is awesome for keeping the log files really small and lean. Then on the right, we have row-based replication, RBR. This sends the result of the command, like the specific rows that actually got changed. This seems way more detailed, and believe me, there's a very good reason for that. And here is where things can get, well, really dangerous. So imagine the master runs this exact command. With statement-based replication, it literally just sends that text, that exact query, over to the slave. But think about it. What if the slave is lagging a bit and runs it, say, 5 seconds later? The now function is going to return a different time, which means it could delete a completely different set of users. And just like that, your data is corrupted. That's the huge risk with SBR. It uses commands that aren't deterministic. In other words, there's no guarantee they'll produce the same result every single time. This is exactly why row-based replication was invented. It completely sidesteps that problem by just sending the specific outcome, hey, delete the user with ID 45, and now delete the one with ID 89. It is 100% consistent, every time. But, and it's a big but, here's the trade-off. If your query updates 1 million rows, your log file is now going to contain 1 million individual row updates. It can become absolutely enormous. You've just traded guaranteed consistency for a ton of disk space and network bandwidth. All right, now for the final and maybe the most critical layer of this whole thing. When a user writes some data, at what exact moment does the master database get to turn around and say, success, we got it, your data's safe? How it answers that question defines the fundamental trade-off between speed and safety. This table lays out the 3 main strategies that systems use. Let's take a look at how each one tries to balance that need for speed against the very real risk of losing data. This is where the life or death decisions for your information are really made. First up, we've got asynchronous mode. In this world, the master gets a write, immediately tells the user, yep, we're good, and then, sends the update to the slave whenever it gets around to it. It is blazing fast, the fastest method possible. But if that master server crashes in those few moments between saying success and actually sending the log update, that data is just gone, poof, vanished into thin air forever. Now, on the complete opposite end of the spectrum, you have synchronous mode. Here, the master is super cautious. It gets a write, sends it to the slave, and then it just waits and waits until the slave writes back and confirms, okay, I have the data safely stored. Only then does it tell the user success. This guarantees zero data loss, but the trade-off is brutal. If even one of your slaves is a little slow or its network connection gets flaky, the master just freezes. It can't confirm any new writes, and your entire application grinds to a halt. And this, of course, brings us to the practical, real-world solution that most people land on: semi-synchronous. You can think of this as the Goldilocks option. Not too risky, not too slow. The master will wait for a confirmation from at least one slave before it gives the all clear. This gives you that critical data durability without letting a single misbehaving slave take your whole system hostage. It's the balance that most modern systems have decided is worth it. So as we start to put all of these pieces together, it becomes painfully clear that there are just no perfect, easy answers here. Every single choice is a compromise. Database replication isn't some simple, solved problem. It's a constant, tricky balancing act that engineers have to manage. So these are the fundamental trade-offs it all boils down to. You have to pick between having nice, small log files or having guaranteed data consistency. You have to balance getting the fastest possible response time against the risk of zero data loss. And you have to decide what's more important: a system that is always available, or one that ensures every last byte of data is durable. As an engineer, you just can't have it all. So the next time you hear someone just casually mention replication, you'll know the real story hiding behind that simple term. You'll know it's this dynamic, complex system defined entirely by critical choices. Which really just leaves one last question. If it were you, if you were building the application, what choices would you make? Which of these trade-offs would be worth it to you?